All right, here is the second part of 606, where we're looking at free body diagrams with centripetal acceleration. And we have here a ball of mass M is swung in a vertical circle with a constant tangential speed. Figure 1 shows the forces exerted on the ball at the top of the circle. So this is the top. Figure 2 shows the forces exerted on the ball at the bottom of the circle. This is going to be the bottom. Which of the following is an expression for the centripetal acceleration of the ball in terms of m, t1, and t2? I pulled this out of the lineup of your multiple choice practice because this is more formula manipulation, and we need some practice with that. We need some instruction on that. But first of all, let's start off and talk about the physics. So at the top, let's talk about the bottom of a circle. So we're spinning something like this, going around, not horizontally, but vertically. And so what happens at the bottom of the circle? So if this is my center, so the center is here. It's too high. So here's the center of my circle. The ball is going to come up and out and around this way. So I need to have a net force pointing towards the center of my circle. Now gravity is going to always act down, and notice in both of these diagrams, the vector for gravity is the same, because gravity is not going to change on this ball. What is going to change is the tension at different parts. Because we're spinning at a constant speed, the tension is going to change. At the bottom, I have to have a pretty big, and I've actually shortened this up a little bit so it fits on my page. On yours, you can definitely see that T2, the tension at the bottom of the circle, is greater than the gravity vector, which gives us a net force towards the center of the circle. Down here, where this is the top of the circle, my center of my circle is going to be here. So I'm going to use a little C to indicate the center. I have the same force of gravity, but you'll notice my tension is much, much smaller. I still need to have a net force pointing down to the center, and it's going to be the same net force because I have the same constant tangential speed. And my radius isn't changing. So we know that FC is equal to MAC, or we could say is equal to M tangential speed over R. The mass isn't changing, the radius isn't changing, the tangential velocity isn't changing. That means I have to have the same centripetal force here as I do here. And what they want us to do is they want us to come up with a new equation that shows this centripetal force, or I'm sorry, centripetal acceleration in terms of mass, tension 1, and tension 2. We have said as we go, anytime you have a system and you have multiple objects or multiple views, you always want to come up with a free body diagram for each scenario and for an equation with each scenario. So let's come up with an equation for the centripetal force here and the centripetal force here. I'm going to switch to, I don't have my pencil with me, shoot. Okay. I'm going to write it incorrectly first, and then I want to show you, I want to fix it, or I want to discuss it. So here, I have centripetal force for this side, and I'm going to have centripetal force for this side. And you might be saying, okay, well, that's going to be T2 minus T1, or minus the force due to gravity, which would be accurate. We're not going to overthink this one. So to get the net force, I need to add up all of my individual forces. Over here, the way that you set this up is going to be important. So off the bat, tell me, or pause the video as you think about, are these vectors going to be positive or negative? Okay, did you pause the video and think about it? The first time, the reason I pulled this problem out of the lineup is the first time I did this problem, I had been doing some force problems before that. And we've been thinking, you know, every time we set up a free body diagram, we're going like, okay, here are my positive directions. When you're doing centripetal force, it doesn't work like that anymore because the force is always pointed towards the center of the circle. Right away, I started to think of this as a negative value because we always say that gravity is pointing down, and it is. But in this case, remember, I always say gravity, the acceleration due to gravity is 9.81 meters per second squared down, or I'll say gravity is down, but I don't give it a sign. Because in this case, that's going to be positive. It's actually going to be positive because it's pointing towards the center of the circle. So instead of writing this as negative, and here it is negative because I have my ball here and it's working in opposite direction, but here it's not. So when I write this expression is going to be force of gravity plus T1. Because we're dealing with a vertical centripetal system. And that is a small detail, but it's important because if you don't have the right signage, you can't even get off the ground. This doesn't apply anymore. You have to be careful because gravity is still down, but our values are not necessarily, because our reference system has changed. Okay, now we can kind of go to work. We know that this is equal to mass. I want to do this. Let's see. Let's put this guy in terms of gravity. So now we're going to do a system of equations. So now that we have our initial equations set up, we've got our free body diagrams, we're going to start doing substitution. So here I'm going to say that centripetal acceleration, force due to gravity is equal to centripetal acceleration minus T1. Actually, I probably could have done that differently. Anyways, I'm going to leave it like that. I also know that centripetal acceleration is equal to mass times centripetal force is equal to mass times centripetal acceleration, and that's T2 minus Fg. Remember what they're asking for is centripetal acceleration in terms of m, T1, and T2. So now I'm going to substitute this in for Fg. So I get mass, I'm going to put that capital, times centripetal acceleration is T2 minus, this is going to be also mass times AC. So I should have written this as mass times AC here, minus T1. And all I have to do now is to put centripetal acceleration by itself in order to come up with the equation that I need. So I'm going to add the opposite, and I get, if I bring this over, that's 2m AC equals T2 plus T1. Then I divide both sides by 2m. I end up with centripetal acceleration equals T2 plus T1 over 2m. You've got this cold? Maybe, probably not. There were a lot of thought leaps here. The first one was that remembering that we have to, when we assign our values, we're not going with just the standard coordinate system anymore. We have to think about where we're going, where the center of a circle is. That changes our signage. Then we had to get some practice, again, writing equations from our free body diagrams, and then we had to practice substitution of equations, and that just takes some practice to get used to. So it turns out that our answer here is D, D1 plus T2 over 2m. But these should feel a little familiar to you, a little bit like maybe an Atwood machine, where again, you have multiple diagrams, multiple equations, and you have to bring them together. Okay, hope that was helpful. Thanks for watching.